Okay, so it's 4 and we'll start today's session. Yeah, so we'll start today's session. So, fortunately, in this session, in this week 10, Professor discussed some of the basics of R, and I don't think there is anything more I can add to that. So, you can, if you want to go through it again, or if you have any doubt, you can ask me in that last two sessions of the introduction to R. Otherwise, we will not be touching upon that. We'll touch upon some of the theory that has been taught, and we'll do some questions. We'll come to R when in the upcoming week or in this Sunday when we have to do some of the programming. Then we'll use R. Or maybe I'll see if we can use Python also in that, for doing all those things. But R is also free, so we'll decide what to do with that. So for today's session, we'll cover only some of the theory and some questions related to that. Okay, so let's start. So in this week 10, mostly we have discussed the topic of digital soil mapping and how do we go about doing that. So what is this digital soil mapping? Basically, when you want your soil properties at any point in a field, right, at a given area in a field, you can't go about getting the soil properties at each of the point. So what do? We collect at some points, and then we perform a kind of an spatial interpolation, and using that, so let's say we got the properties at some of these red points, and now we want to know how what will be the property of the soil at some other point. So we'll perform some kind of spatial interpolation, and that will be, so we have seen in some empirical methods it will be a weighted average with respect to the other points that we know. In stochastic, it can be the weights can be obtained from different methods. So doing that and representing it on a map is what is called digital soil mapping. Okay, so let's write the definition to make it more formal. Yeah. So computer assisted. It is computer assisted production of digitally interpolated or digital interpolated map of soil properties. Now it can be soil class, soil type, organic content, iron content. So any of this can be inside the soil properties. Now, how do we go about doing this? We use mathematical, empirical, and statistical tool, and we use some auxiliary data. What is this auxiliary data? So here is something interesting. When the method that I talked about just now, that was just simple interpolation. In that, you won't have 100% confidence on the reading at this point based on these points, because let's say if there is a sand here. Oh, so it's doing some kind of magic. Okay. If there is a sand in this area and we took the readings here in the, and we are just using our mechanistic model of empirical model of getting the soil property at this point, and by luck or by some bad luck there is a river here, then you will get some kind of soil property at this point, right? Even though there is um, no soil there. So to avoid that kind of problem, we use some auxiliary data. What can that be? It can be GIS image, or sorry, let's say it can be a DEM file, or it can be your satellite image. So we have already seen, uh, sorry, we have already seen that in the satellite image we can easily distinguish between water bodies and between the soil by using the infrared. If you remember correctly, if you don't remember, you can go back and check that. So we use some kind of auxiliary data so that we have a relation between, we don't do a very abrupt kind of wrong prediction. And even in soil itself, the sand will be more reflective, whereas the clay will be less reflective. So this can help us in doing that kind of differentiation also. So along with the experimental data that you have, when you use the satellite data and distinguish this area more into, let's say, different class of soil, then your classification can be even more accurate. So this is what is basically goes on in the digital soil map. What is digital soil map? It is just a visualization. So I'll just write DS map here. It is visualization of all the data that you have obtained in the digital soil mapping. Okay. Now the question comes that why do we need this kind of digital soil mapping? So as I started with the topic that we want the variation of our soil property in a given area, then we can't go about getting the variation at each point in that area because it is going to be costly, it is going to be time taking, right? And if the area is so big, it's just next to impossible to do all those tests in an area. So when you have a digital soil map based on the process of getting data at some reliable points, then you can be confident that you have a pretty good estimate of the soil properties in that area with doing much less work. So it is cost effective first. It is, it can be used in policy making decisions, and if you use stochastic methods, it can even give you uncertainty in the prediction. So in that case, so let's say you are designing some kind of well, and you need to know hydraulic conductivity in this area, in this area surrounding this well. Now, when you do stochastic digital soil mapping and you get in some way this hydraulic conductivity, in no way you are going to get this conductivity. I'm just saying a hypothetical case. So, if you get a stochastic estimate, then you will have a minimum value and a maximum value, and you can design for the most critical part, design for the K critical, so that your system doesn't fail in case of flood and it also doesn't fail in case of drought. So this can be helpful in that scenario also. Okay, so I hope you understand this. Now let's move on to the some of the basic or fundamental digital soil map functions or models that were given and are obtained from the literature. So we have Jenny 1941, a pretty basic model. She gave the soil property based on the climate change, or sorry, based on the climate. The organism is nothing, let me write here. Climate organism is nothing but the land use, land cover. Then we have relief, that is just the information of the terrain. And we have our parent material and time. Okay, so just a minute. Parent material meaning the geological map, and then time. So she didn't consider the location, and her model was empirical, which was later on corrected by MC Bratney in 2003. So they gave a model which gave the error also in the estimation of the soil properties. So basically, just we need to know just the equation, because it's not very important to get into the details of these models. Which just we need to know what is the input they used. So they used the soil property at that same location, then the climate, then land use, land cover. This is organism, this is relief, the terrain, this is the parent material, geological map. Then they used age, and they used the location. So something different from the Jenny model. And this, sorry, soil properties at the same location is also one of the differences between the Jenny model and the Bretney et al. Model. Okay, so just keep this in mind, because we'll have some questions based on this. Okay, now when we talk about digital soil mapping, we saw that there are some auxiliary data that is required to make the prediction more reliable. Now, this can be your digital elevation map. So I will discuss only few of the examples, and can be your satellite map. So let's look at digital elevation map, that is DEM. Okay, so what does this digital elevation map show? So when you look from the satellite to the ground, you will see trees, you will see buildings, right? And you will see water in the rivers if there is any water left. So we are not interested in these surface objects. We want just the bare ground profile. After removing all the surface objects, we want the bare ground profile, or a bare ground topographic surface. That is the DEM. So there are different techniques to remove these trees and buildings. So you don't need to worry about those things. Okay. So how can this be useful? Just intuitively, let's talk about how can a DEM be useful for us. So here's a very general kind of example of, if you go to a beach, what do you see on the beach? So let's say this is a sea, and next to sea, everything almost always we have sand, right? Because in sides of the river also it is sand, because the water crushes the rocks and then they get settled on the sides of the ocean, or seas, or the river. So if you have a topographical map, a dam map, and you see that you have rivers, or you have an area which is next to your sea, then you can be a little bit more certain that some of the area will be sand, and when you come to more to the inland, then you will have some clay, silt, loam, and all that. And also when you look at mountains, mostly, or more often than not, the mountains are made up of clay materials, clay, silt, and loam, but mostly clay. because if you make mountains with sand, if you have seen, it is not we go to the beach and we try to wet the sand and make the sand castles, right? So it only works because of the superficial adhesion between the sand particles when they are wet. But when the mountain is standing for so long, then they are because of the cohesion strength between the clay materials. So then this can also kind of help you in identifying the soil class using this digital soil mapping. Okay, that's just one of the very basic ways to explain the importance of them in this digital soil map. Then we can use satellite, and as always, we have seen that studying the information of from the satellite and making some inferences comes under this GIS, remote sensing, right? That is geographical information system. One more of the auxiliary inputs that is being used in the model. Okay, now what kind of data types do we have in the GIS? So basically, we have raster data and we have vector data. Raster data is in the form of grid. So you would have seen, or we have talked about the images that we see on your screen, on our screens. They are made up of pixels, and each pixel takes some area, some grid, and shows different intensity of red, green, and blue, right? And then we see some color. So you can say that your screen is a raster, and the images from the satellite are raster. But what about vector data? So vector data is point, line, or polygon. So in case of point, we just have one point, but that is not possible in case of raster. You will have, even if you go very fine resolution, still you will have a area. In case of vector, if you say a point, it is a point. If you say a line, it is a collection of points. And if you say a polygon, then it means there is a line that uh, closes and makes an area. So you define that by the boundary. So they are these two basic type of data that are used in the GIS. Now, when which data is useful? Because you cannot get your satellite images in vector data, right? It will be very, very costly and frankly impossible to get. So then how do we go about choosing where do we want vector data and where do we want raster data? So if you have scale, if you want to do on a small scale, if your area of application is small, let me write it here, how to choose. If area of application or study is small, then we go for vector data. Why? Because these raster data that usually we get from the satellite, if they have even the finest resolution is 1 meter by 1 meter, if you say 1 meter by 1 meter, then also you have the properties of an area averaged in a square of 1 meter square by 1 meter by 1 meter. Where so that can cause some kind of overestimation, underestimation in your prediction when you use that in a small area. But in a small area, if you want to use raster, let's say I have a 10 meter by 10 meter plot, and I cannot use raster here, right? Because I will have 1 meter by 1 meter, and then my problem is overly simplified. So in that case, we need a very fine resolution raster, let's say 0.01 meter, and that is like frankly not very feasible to get. So in that case, we use vector data. So let's say if I want to represent a well in this plot, then I can an injection well, like I am pumping something from the plot, or I am pumping something out from this plot, then I can represent it using a point in a vector data. Whereas if I were to use a raster, then superficially I am making the area of pumping very big and creating kind of uncertainties in the predictions thereafter. So this area of application is one of the issue. Then another issue is, so you can say area of application or scalability. So if you want to go from high scale to low scale, vector data format is preferred. And why it is preferred even more in small areas is because if you have a higher resolution raster, they have they will have very high size. So this movement and sharing of this very high size data, very big data, is not also feasible. So to make our life easy, we can use vector data when we need fine resolution. Okay, so these are some of the interesting topics. Then after that, we have coordinate system. So when we are sharing this data, so why did we even need this coordinate system? When we are sharing these soil maps and uh, with people on the different side of the globe, then to make a common reference point, we need something that is constant. So that is why this geographical coordinate system, where we can have a reference to each point, was developed. So let's see what are the features or what are the properties of this geographical coordinate system. So if you have seen a globe, you will see that there are vertical lines going like this, and there will be horizontal lines. Oh, now I have a question. Many people get confused, many adults even get confused, that what is the name for these vertical lines and what is the name for the horizontal line. So first you tell A and B. What is the name of the vertical line that is shown in the globe? Okay. So probably it is too simple question then. So vertical lines are nothing but your, sorry, let me write it here. Yeah. So vertical lines are nothing but your longitude, and horizontal lines are your latitude. So your longitude can vary from minus 80 degree, so or even you can say 80-degree west, 180-degree west to 180-degree east, and your latitude can vary from 0 at the equator to 90-degree north, 90-degree south, or 90-degree north. So you can even say by minus 90 to 90 and minus 180 to 180. And I have a question that what do you guys think? So we are having this 180 degree The longitude is varying from minus 180 to 180, right? So where do you think this 0 degree is? Where is the 0 degree longitude? 0 degree latitude is the equator, that is fine. Where is the 0 degree longitude? So this 0 degree longitude, if I am correct, passes through the Great Britain. So if you can go ahead in the internet and check that. So just for fun. Okay. Now this is the geographical coordinate system. We are representing the points on the surface of the globe using longitude and latitude. The unit of longitude and latitude is degree. Degree, minutes, seconds. It can it can go can go on. And this representation shows the Earth as a spheroid or ellipsoid. Whereas, if you see in the maps, in the books that you see, your globe looks like a plane surface, right? So I hope none of the people in the class are assuming that the Earth is flat. I think that is only a Western kind of problem. We Indians should not have to deal with that. So this representation of a flat Earth in the maps that we see is done using the UTM coordinate system. What is the full form of UTM? Universal Transverse Mercator. I don't know if I'm pronouncing the last word right. We will just call it UTM. There are, so how do we get this from the spheroid surface of the Earth? How do we get this plane surface? So if you look at the globe carefully, you have, and you want divide it into 60 parts, 60 equal parts, starting from the north pole to the south pole. You will have strips that are thin at the top, increase near the equator, and then decrease again towards the south pole. So these are the strips, and these individual strips, when you flatten them out, like when you increase this top area and decrease this equator area, then you get rectangular strips. So your rectangular or the flat image of the Earth that you see in the maps, they are coming by doing some grid transformation of your actual globe. And there is a nice package in Python that does the to and fro from the UTM coordinate system to the this geographical lat long coordinate system. So the unit of this lat long the UTM coordinate system is in meters. So you will be having, let's say you have a reference point here on this particular plane, then you have some x distance or y distance from here and x distance from here, from this reference point. Then if you want to convert it into a lat long, first you need to know the lat long of this reference point, and then using these distances of y and x, you can get the uh, lat long position of this point in the uh, earth kind of geographical coordinate system. So how many, so when we divide this earth, how many planes have we divided this earth into? So that is one of the questions that can be asked, that if you are doing this kind of transformation in a in, in this kind of globe strip and making into a plane, so how many standards are there, how many these kind of strips are there? So there are 60 UTM strips, or we call it as UTM zones. and each zone, since I said symmetric and equally divided, so each zone is having a 6-degree longitude area. So you have this globe and you are dividing this, making it division in this kind of strip. So this angle, if you see, this angle that we talked about, the horizontal angle, that is the longitude, that is 6 degree for each of these strips, right? So I hope that is clear. So yeah, now one another question that I think probably everyone should know. So I said we have UTM zones, 60 UTM zones. So basically, our Earth is divided into this kind of vertical strips that are 1, 2, 3, and then 60 on this side. So, which under which UTM zones does this our India lie? India lies under which UTM zone? So, you guys can Google it. Not now, right? Not now. You guys can Google it if you are watching this video. But if you look at this map, our India lies from UTM zone 42 to very small part of Arunachal Pradesh going to UTM zone 47. So this is the vertical strip. Starts from 42, 43, 44, 45, 46, and 47. So I don't want to draw and disrespect our map, so I will not do that. I'll just make a rough sketch. So this is how the map looks like. Okay. So let me correct it. Yeah, this is how it looks like. Okay. You can correct me if I'm wrong with that information. Okay, now, so we have seen till now our digital soil map and some of the auxiliary data that we use for doing the digital soil mapping. And we have seen that one of the auxiliary data, that is this satellite, that the satellite images that we use comes under this geographical information system, and what are the units of the information, or what is the data type that exists in this satellite image system. So how do we, that there arises a problem actually when you want to use satellite information and your experimental data together to perform this kind of digital soil mapping. Then there is a fundamental problem, and that is, see, you have an image from the satellite. So let's say you have a big plot and you got the image from the satellite. That image is going to be by default in a raster format with some grid size. Let's say it is 10 meter by 10 meter. Okay. And you perform some experiments, or you have some experimental data from the literature, and you have performed the experiment at some points. Let's say the red dots denote the locations where you have performed the experiment. You have performed sufficient amount of experiments and covered the whole area. But still, there is a problem that inside this 10 meter by 10 meter square, if you have performed only one experiment at some point, at some corner of this point, then this data cannot be a representative of the soil properties in that particular grid, right? So, how do we get out from this problem? One way is to get a finer grid. So if you are able to get a finer grid and make that point into one of its own grid, then you can very nicely perform the interpolation and it is fine. And you can assign that whole grid that this same property. But as I have discussed prior to this, that is not feasible and it is going to cost too much to perform that kind of satellite mapping. So then what is an alternative? The alternative is to perform experiments. So if you are performing experiment at one point, so in at this point, if you are performing experiment at this point, so you have to perform two or three experiments sampling at the neighboring points also, so that this information that you are getting is not just for that one point. The average of those experiments can be used as the representative information for that particular grid. So if you have 10-meter by 10-meter grid, if you know somehow the resolution of the grid, then what you do, you perform the experiments, let's say at in a triangle that is circumscribed by that square grid, or at the some distance away from the corners of the square and in the center of the square. So if you do that, then the average of the soil properties at this particular grid can be considered very nicely as an representative property of soil in that grid. If you But there is another problem. If you do this, then the limitation arises then when you are doing a validation from of your model, of your inference from your obtained results, and when you validate it with using point data, then there can be a certain discrepancy. So that can be one of the problem. But still, this model where you use the average of the experimental data in from the neighboring points, and you use that to make some inferences or train your model, this will still be considered more acceptable than if you were to make a finer grid, or if you were to use one point only for one grid. So this is what was discussed as the problem with the support file, if you remember in the PPT. So it is raster versus vector. How to use both of them together. Okay. So now let's go ahead. Yeah. So there is, in this digital soil mapping, there is a basic mathematical principle behind doing all this spatial interpolation, that is called geostatistics, another field of study. So basically, this digital soil mapping is nothing but using this geostatistics for soil, right? So if I were to define this, it is nothing but analytical production of high resolution, means we are doing some kind of interpolation by using field observation and computer model and auxiliary data. See, pardon my handwriting because you all have this PPTs, so I don't bother writing nicely. I just try to write fast and cover more ground. Yeah. So the purpose of geostatistics, we can say it is same as the digital soil mapping, that we want to get an interpolation of the data where we have not performed the experiment. Then we we need to get the uncertainty estimate, because the Jenny model 1941 was not giving us the uncertainty estimate. Then we use the auxiliary files to make a more reliable estimate of the soil property. Now in this geostatistics, there are two type of models. One is deterministic and another one is stochastic. When we say deterministic, then we mean that one input can only have one output. It is an empirical equation or empirical model. So it is a fully defined, well defined parametric kind of model with no randomness, and which if you give one input, you are going to get one output. But in case of stochastic model, it retains some inherent randomness. And even if you give same input twice, it can produce different output. And that is uh, the extent of that randomness is decided by which probability function you are using to model the randomness. Okay, so then we will discuss one of the deterministic model, that was inverse distance interpolation, and the one of the stochastic model, which is very similar to this inverse squared interpolation, that is the Kriging model. So let's start with our empirical model. We have inverse distance interpolation. Okay, so basically when we have some field data at, let's say, red points, and we want to get the field data at this black points. So the principle behind this kind of interpolation is that i- points which are close by, so let me write it, points which are close by will have similar properties. Okay, so you can even say that this is the basic working principle of this whole geostatic spatial interpolation. If this is not valid, there is no point in doing any kind of spatial interpolation. So this is the backbone of this geostatistic spatial interpolation. So now we want to know the property at this black point. So what we do, we compute a weighted property. We say that this property is going to be a weighted sum of the property at these points. Now the difference in choosing the weights is going to cause the difference in the name of these methods. So when we say inverse distance interpolation, then the weights are going to be the inverse of the distance of this point with the other points. So So the basic governing equation, it will be, if you want a property, let's say y hat at a point, it is going to be a weighted sum wi into yi, where yi is the known property at the red points, and we do a sum over all the points. So if you say n, you have capital N number of points, then you do this and you get the weighted sum of the properties, and you say that this is the my property at this particular point. And in case of inverse distance interpolation, this wi is nothing but 1 by dix divided by sum of 1 by dix, where dix is the distance of point x with all the other points, that is I varying from 1 to n, and x is the point where you want to know. Okay, that is dis, and beta is just a parameter of the model. So if you have beta is greater than 1, then you are giving weightage to you are giving importance to this distance of the point from the known points. If your beta is 0, if you look at it carefully, if the beta is 0, then this 1 by dix becomes just 1. So anything power 0 is 1. So in that case, you are not giving importance to the distance, and you are just doing arithmetic mean of the properties that you have at these known points. So you can have this you can choose different values of beta and try which and see which value gives the most feasible result, and then based on that we can choose beta. But that is also one of the shortcomings of this method, that the parameter beta is decided by the user. It is not objectively calculated, and that's where this Kriging method is comes into help. So this is a stochastic method. Oh, just a minute, this, yeah, stochastic method. So if you look at just the equation is going to be same as the equation, similar or very much same as the equation in case of inverse distance interpolation. But the weights that for inverse distance interpolation, which were obtained by just calculating the distance of the point from these known points, this weight is now calculated using stochastic method and a graph that is called variogram. So we'll see some of the properties of the variogram. We don't have to go into much of the detail of that. So if we look at the equation, they are virtually not different from the equation of inverse or the empirical equation of the inverse distance interpolation. Just in the end, we just add some kind of randomness to the obtained value. Okay, so what does this variogram captures? Variogram captures the variation of variogram captures the variation of semivariance. It is the difference between the properties with the distance between each point. So let's say if you have collected a lot of points, and variogram will be then made for all these kind of distances. Let's see some of the basic features of this variogram. Okay, so you have a plot something like this. So it is observed that this your semi variance, and then the distance follows this kind of behavior, that the semi variance first increases and then it becomes saturated. This portion from where the plot starts in the y axis, this is the unexplained variation. So the data that you have cannot explain this variation, and this is called nugget. The total the maximum semi variance that is explained is called the sill. The difference between the maximum and the sill is the explained, sorry, explained diversity by your data. So that is like the partial sill you can call. And this is the range. So the you can say the areal extent, kind of the representation of the areal extent of the measurement that you have taken. Okay, so that's all that was interesting for this week's theory content. Now let's go on to some of the questions. So I will wait for, let's say, a second or two for you guys to answer, and then I'll try to explain what is the answer if you're not correct in that. So which is not a part of Jenny's five-factor soil formation? So we saw Jenny's model, 1941 model. So what is the answer? Climate, organism, parent material, or crop management? Which was not the part of Jenny's five-factor soil formation? D. Very good. As a matter of fact, it was not a part of, I think, the 2003 model also, right? We have covered crop management in the previous session, I think. Now, LiDAR is used for generating accurate dash about the Earth's surface and target object. Now, what do we construct using LiDAR? Is it a 2D information, 3D information, micromorphological information, or biochemical information? Is some of the options are just absurd and we can be removed. Like we cannot have a biochemical information. So, what do you think? Basically, what LiDAR does is it measures the distance. So in the PPT, sir showed that there is a plane on which they will install a LiDAR sensor. And if this plane is moving on a constant height, then it will be able to capture the height variations below it. And if at all it is possible to keep the plane at the same height, and we will get a nice 3D, three-dimensional information about the object or the surface that we, yes, that we want. So it is 3D. Now a DEM is representation of what in the surface of the earth. So in the starting of the session I said that when you look at the earth's surface from the satellite, you will see trees, you will see buildings, right? Yes, exactly. So Gulshan has pointed out correctly. So we will remove all these surface objects and we'll just see the representation of bare ground. Now, which is the example of raster data? So when you have when you are dealing with uh, GIS, I forgot the full form, Geographical Information System. So in that case, you have two type of data, that is raster and vector, right? So what which of these is an example of a raster data type? See, vector had, yes, vector had point and line, that is nothing but collection of point, and area, that is defined by the collection of line that is making a boundary. right? Whereas raster is a graded kind of data format. Correct. Okay. So, okay, we have some substantial questions, right? Yeah. Which of the following statements is false? In a GIS, a vector layer. So you can read and you can try to solve. I will read and I will try to explain each of the lines. We have to choose a false statement. In a GIS, a vector layer is stored in a computer as a grid cell. Okay, so basically, our first statement itself is false because a vector layer is a collection of line or a point, right? So this itself is false. But still, let's read the other three. Raster data works with pixels. Vector data consists of coordinates. Correct? Pixels are nothing but gridded data. Vector have wide flexibility in scale, but raster does not. Correct? See, your raster will have some kind of resolution. So you cannot go finer within that resolution, because if you do that, then you will have only single property for the whole area. Whereas vector will be a point. So no matter you zoom in how much, you that point will still be a point. Raster file size can result so raster file size can result larger than vector data sets with the same phenomena. Correct? If you want to capture each and every point in an area, then if you have a raster style data type, it will be a very huge data size, whereas in case of vector it will be small. So only the first point was correct. Are you all following? Okay, good. Now, which of the following statement is true? Now we have to get the true statement. So I will again read the lines, and then you, if you know the answer priorly, you can put it in the comment. A geographical coordinate system is a system that uses two-dimensional spherical surface. So, geographical coordinate system which represents a 3D surface, how can it use a two-dimensional spherical surface? That is not correct. Now, a spheroid is a sphere that is based on circle. It may look very, you may feel like, okay, this is correct. But remember, Earth's space, our Earth is not a sphere. It is an ellipsoid or a spheroid, which is based on not a circle but ellipse. So this is also not correct. Then the coordinate system can be defined either by sphere or a spheroid approximation of the Earth's shape. So the a coordinate system can be defined either by either a sphere or a spheroid approximation of Earth's shape. That seems to be correct, but let's for safety, let's read the last point. Point vector is a set of values that defines the point of the spheroid relative to the center of the Earth. So let's see. What do you guys think? Which one is correct? Is it the C or the D? Do you have an answer, Gulshan or Prachi? Confusing. Right. So point vector. So okay. What about Miss Prachi or Mrs. Prachi? I don't know. Okay. So the correct answer for this is C. A coordinate system can be defined either a sphere or a spheroid approximation of Earth's surface. Even though it will be wrong, we can define that. But a point vector is a set of values that defines the position of a spheroid relative to the center of the earth. The spheroid is a 3D object. So it is very difficult to define that position with the point vector. I agree that this is confusing, but this looks more correct. So we'll go with that logic in this case. Is that fine? Because here they are not talking about accuracy. They are saying, but only that we can be defined. Okay, we'll go to next question. Okay, so I'm not getting any response. We'll go to next question. So UTM system consists of how many zones, and each zone has how much degree in longitude? 66. Very good. D. So our Earth is divided into these kind of strips, which where these strips are 60 in number, and this angle is 6 degree, and they are expanded and made into rectangle to be shown in the flat maps that we see in the books, which is the integral part of geostatistics. So if you remember, I was saying that we all of these, correct. So we have field observations, we have auxiliary information, that is the GIS maps. Then we have computer program to fit the model to get the values. Right. So okay, this is the question now. Dash model possesses some inheritance randomness. The same set of parameter values and initial conditions will lead to an ensemble of different outputs. So, in our geostatistics, if you remember, we have two models. One is mechanistic or mechanical, that were the empirical models, and other one was stochastic. Yes. No, 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 no. So, in this case, the answer will be B, because deterministic models, that were the empirical models, they will give same output for the same input. Because their parameters are well defined, they won't show any kind of randomness. Whereas stochastic will show randomness, even if you give the same input, they can give different output. Okay. Now, semivariance is a measure of dash between two observations as a function of the distance between them. See, here if you see, the options are very absurd. So we can quickly uh, tell the answer for this, even if we have no idea. See, we do the semi variance, or the name of the plot. If you remember, it was variogram. We use this in our kriging kind of spatial interpolation, right? So the semi variance is going to be the difference between the spatial dependence. In that itself, the height will be covered, right? If there is a difference in the height will be covered in that. So we'll say A. You remember the variogram? We had distance, and we had semi variance, and we plotted like the distance between each of the points, each of the consecutive group of points, and then we plotted the semi variance, which kind of saturated. So there we are checking for the spatial dependence of the two observations. Okay, now what is the next question? Which of the following statement is false? The difference between the difference between the sill and nugget represents the amount of observed variation that can be explained by the distance between observation. So, what do you think? Is it true or false? True. Very good. So, we saw that this is nugget, this is sill, and the difference is the partial sill, which is which is the portion which is explained by the model, and that's what is written in this point. But we have to get the false. Now, a standard version of kriging is called ordinary kriging. So this is again true. Range is point at which semivariance stops decreasing. Now in this plot, let me draw this plot nicely. I want you guys to tell me whether it is A, B, C, which one is range. A, B, C, D. Which one do you think is range? So we quickly went through this range. Yeah, D, correct. But what is happening to the semivariance at this range? Is it decreasing before this? No, right? Semivariance was increasing and then it became constant. So this point that it stops decreasing is wrong. Let's read the next one. No estimate of model error is available and arbitrary empirical models are used in mechanical models. That is correct. See, there is no model error available in case of empirical models, and they are used in they are also part of mechanical models. Arbitrary model error is only available in stochastic model. That is the uncertainty in the prediction that they give. Okay, so which of the following statement is true? Uh, this is not the question that I. Yeah, this question you guys can answer. I'm not very interested in this question. This R can be freely downloaded from something. Then the R started in 2011. Plots tab in R Studio is used by typing R commands. The console window in RStudio is the place where R is waiting for you to tell to what to do and where it still show the results of the command. Where it will show the results of the command. So you guys, R can be freely downloaded, right? So that is the first sentence itself is correct. That is not very kind of useful question for us, so we'll just ignore this question. So until these questions, is there any doubt? Because after that only the introduction to R is left, and I think that is covered nicely in such session. And we look at R and preferably, I want to see if the things that have been done in the R in the week tutorials, that can that be done in Python. So if they can be done in Python, I'll try to show them in Python. So basically, I'm saying that if you want to go back to the R, how to use R, you can just look at search videos because that is very trivial. Is that okay? Okay. So then that's all there was for today's session. We went through the digital soil map, then what are the auxiliary data for that, Then in the auxiliary data, to get the satellite, we went through the GIS and the different type of datas that are available in GIS and their formats. Then we saw the geostatistics and the uh, two variations of the spatial interpolation that were discussed in this week. And then we looked at some of the examples. So I think we have covered what was covered in this week. And yeah, if you don't have any doubt, then we'll be yeah we'll end this session for today. Prachi, you have any doubt? You didn't say much in this session.
I missed a few minutes. That's it.
Okay, no issues. You can watch the video. I'll upload it.
Okay. That's it.
Okay then. Yeah.
Anyway, it's fine.
Okay, yeah.
Any how more means this live session we have to attend before the exam?
So the date of exam is finalized.
I think that is 30th April.
30th April.
We
Okay.
have the
So then there will be another session on this Sunday, and yeah, we'll have two more sessions before the exam.
yes, yes, because
So
this is week 10, I
yes,
think.
this is week 10. Yes. So I could not take the session last week, so this is a postpone of that session.
Yeah, actually, I also left. Means I was waiting for last week. So today also I just missed the means few minutes. I forgot about this one.
Oh, no issues, no issues.
Yeah,
Sorry
because
about
this
that.
live session, I think we were discussing more about different questions also, not exactly the assignment question. I think.
Yes, yes, yes. We'll discuss different questions also. Yes.
Yes, yes. Okay, thank you.
Thank you. Okay, then. Thanks, guys. We'll end the session for today.